predicting how molecular speed distribution changes with temperature and molar mass. So essentially, we're looking at the shape of the distribution curve for the speeds of our gas molecules. So what I want you to look for is like, hang on, that's a straight line. I don't want that. I want a nice, just let me draw something with a pencil. Okay, so this may not be beautiful, but you're looking for a nice kind of Boltzmann distribution, a bit like this. Okay, it's usually got a bit of a longer tail. So this narrow shape curve at lower speeds is what you'll typically see at low temperatures, okay, or high molar mass, okay? Because remember, kinetic energy is proportionate to temperature, okay, and it is inversely proportionate to molar mass. So that's 1 over the molar mass. The heavier the gas is, the slower it's going to move. So let me just draw my little proportionality thing. So it's proportionate to temperature and inversely proportionate to molar mass. So this kind of distribution is going to be what you see at low temperatures and high molar masses. If we have a gas where it's able to access higher kinetic energies, what you're going to see is that curve is kind of like going to broaden out, okay? And the gas molecules are going to reach higher speeds, okay? So we're going to have this long, long tail accessing higher speeds, but it's going to flatten slightly, okay? Because you've got a wider distribution of speeds. So we'll see this happening, if I can change back to my pencil, at higher temperature and lower molar masses, because lighter particles are going to travel faster. So that is basically the kind of shapes we're looking at. So what we've got to do first of all is spot the difference with this particular sample. So the one on the left is going to correspond to this left-hand slider. So as you can see, don't care how many moles we have, but the identity of the gas is all the same. Pressure is all the same. Doesn't matter how many moles, what the pressure is. All we're looking at is the proportionality between kinetic energy and temperature and molar mass, okay? Number of moles, pressure does not affect the kinetic energy. So the only difference we see here is going to be in the temperatures, okay? So the hottest one is going to be A. So A is going to correspond to this kind of shape here. The coldest one is B, and in the middle we have C. So we're going to have, if I draw a sort of intermediate line in here, I guess, to kind of show in between the two. This would be my B line, okay? So, well, not B in this particular case. My medium temperature is the orange, okay? So in this case, A is going to be my hot line, okay? So this is going to be at hot temperatures, this color, okay? Go on down here. And then my coldest will be B, so that is going to have this same shape as this green one here. And then the one in between is 242, so that is going to be the same kind of shape as the orange one on the plot that I've drawn down here. So let's try and find that picture, okay? So I want A to be hottest, okay? See, that is not the right shape, okay? See these little bumps here? We're going to actually do some plots that look like this is the distribution of the basically it's a representation of atomic orbitals, okay? We're going to get there in a little bit, but where our electrons can be. That's the wrong shape. This is the right shape. Is it in the right order though? So we're expecting the hottest to be A, and there it is B. So those are the right shapes with the wrong labels, wrong shapes, wrong shapes. So what have we got here? So A should be the hottest, that's this one, and B should be the coldest, that's that one, and C should be in the middle. Okay, so this is the correct order for here. Okay, so then let's look at this second group here. So this time they're all at the same temperature and they're all at the same pressure. Okay, so again, pressure doesn't matter anyway. Temperature, they're all at the same temperature. So the only difference is the composition, okay? So we've got to look at like what's lightest and what's heaviest. So if you need to, pull out your periodic table, okay? So I know that helium has the lowest molar mass, okay? So that is going to be able to get to the highest kinetic energy. So that is going to correspond, if I can change my pencil, to this color on my graph down here. So helium is the lightest. And then next up, we got neon. That's going to be the one like in the middle, because out of these three, krypton is the heaviest. So krypton is going to be the sort of low temperature shape line here. So I would expect F, then E, then D. So let's find it. Those are the wrong shapes. Well, kind of the right shapes, but they don't sit like they're not going up to the right. The curve is okay, but it's not changing the peak speed, right? Which we know it's going to change. Okay, that again is not flattening. Okay. So these are the right shapes, and I want F should be this tall, skinny one at lower speeds, and E in the middle, then D. So this is the correct one. Let's just see what other horrible options we had. Again, these are the right shapes, but the wrong labels compared to our actual compositions. So we need to go back to this one right here. Okay. So that's how you reason that one out.